Hello, welcome. In this short video, let us look at the relation between the Fourier transform of an actual sequence and then its sampled version and the reconstructed spectra from a finite sequence corresponding to this data. That is given the signal x of n equal to a power n u of n. So this is the actual signal. It's a signal equal to a power n into u of n for values of a between 0 and 1. Now let us look at the Fourier transform of this signal. That is x of omega is given by summation for all values of n x of n e power minus j omega n, and for this particular signal this is equal to summation n is equal to 0 to infinity a power n e power minus j omega n, and then applying the geometric series, that is sum of infinite geometric series, is equal to 1 by 1 minus a into e power minus j omega. So this is our actual Fourier transform of the given sequence x of n equal to a power n into u of n. That is the true sequence. Now in reality we might not have access to all this actual true sequence or its Fourier transform. So you might only have sampled version of this spectrum. That is, we might only have x of omega k, where omega k is equal to 2 pi k by n. That is, we sample the frequency or the spectrum at n intervals. So the frequencies are 2 pi k by n, where k is from 0 to n minus 1. K is from 0 to n minus 1. So this is the sampled spectrum. Now we have x of omega k is equal to 1 by 1 minus a into e power minus j omega k. So this is our equation 1. So x of omega k, that is the sampled spectrum, is given by, it is a discrete spectrum given by 1 minus a into e power minus j omega k, where omega k is 2 pi k by capital N. Now the sequence corresponding to this x of omega k. Now consider the sequence corresponding to this x of omega k. Sequence corresponding to x of omega k. So since we applied frequency domain sampling, that is, instead of a continuous values of omega, we have discrete values of omega k from with k equal to 0 to n minus 1 and omega k given by 2 pi k by n. The corresponding time domain sequence is given by xp of n, which is like a periodic sequence with a definition equal to summation with all values of L, and the signal is given by x of n minus Ln. It's like a folded version of x of n or a aliased version of the x of n. So this value is going to be equal to summation over L, and x of n minus L minus 1, x of n minus L into 1 is given by a power n and is replaced by n minus Ln and u of n minus Ln. So that is the definition of x of n. So we apply that in this folding or this definition of xp of n. And since xp of n is a periodic sequence, only unique values of xp of n are in the interval from 0 to n minus 1, and outside this interval are all basically repetitions of the values in this interval. So we only need to consider the values from 0 to n minus 1, and this value of n minus L into n, this value is non-zero only when n is greater than or equal to L into n. So L has to be from minus infinity to 0. For any other values, that is for L is equal to 1, for example, u of n minus n will be equal to 0 because n is between 0 and n minus 1, and if you put L equal to 1, it will be u of for example 0 minus n, or u of minus n, which is 0, or u of 1 minus n, which is also 0, and so on. So the values of L are from minus infinity to 0. So based on this logic, xp of n is equal to summation L is equal to minus infinity to 0 a power n minus L into n. So a power n is basically an independent component, so we bring it outside. So we have summation L equal to minus infinity to 0 a power minus Ln. Now we replace L with minus m, so the limits will be 0 to infinity. So this is a power n summation m equal to 0 to infinity a power n, and then we have L replaced by minus m. So a power n power m. So obviously this should be equal to a power n divided by 1 minus a power capital N. So that is the sequence xp of n. So that means xp of n is equal to a power n by 1 minus a power n, and the actual sequence x of n is a power n into u of n. So clearly there is an extra factor 1 by a power, there is an extra factor 1 by 1 minus a power n. This is due to aliasing. It is due to this formula. Now next we can also notice that as the value of capital N goes to infinity, this xp of n actually becomes a power n. So that means as the signal xp of n becomes a periodic, xp of n will be same as x of n. Now in a general case, when n is finite, then we define a sequence of length n, that is x hat of n, can be defined as xp of n for only values of n between 0 and n minus 1, and it will be 0 elsewhere. So that is the x hat of n, which is like the x hat of n is basically the aliased sequence of finite duration. So x hat of n is xp of n only in the interval from 0 to n minus 1, and it will be 0 elsewhere. Now let us look at the Fourier transform of x hat of n. That is, x hat of omega is given by summation for all values of n, x hat of n e power minus j omega n. And since x hat of n is 0 outside the interval 0 to n minus 1, the summation can be restricted to 0 to n minus 1, and x hat of n can be replaced by a power n by 1 minus a in power capital N e power minus j omega n. And since this is a geometric series of finite duration, the value is given by a power 1 by 1 minus a power n summation n equal to 0 to n minus 1, and then we have a into e power minus j omega whole power n. So that is a geometric series of finite duration. Therefore x hat of omega is given by 1 by 1 minus a power n, that is the factor, and then we have 1 minus a power n e power minus j omega capital N, and then divided by 1 minus a into e power minus j omega. So that is our x hat of omega. That is the Fourier transform of this finite sequence. Now when we sample this sequence, that is at omega replaced by omega k, that is when we compute the values of this Fourier transform at discrete locations omega k, that is x hat of omega k, and omega k is basically 2 pi k by capital N. So this should be equal to 1 by 1 minus a power n, and then 1 minus a power n e power minus j omega k into n, and then divided by 1 minus a into e power minus j omega k. And since omega k is equal to 2 pi k by capital N, this basically is equal to 1, that is e power minus j 2 pi k, which is going to be 1. So x hat of omega k is indeed equal to 1 by 1 minus a into e power minus j omega k. And if you go back, we can clearly see that x of omega k, that is the original sampled version of the original Fourier transform. It is the sampled version of the original Fourier transform x of omega k. So we can clearly see that the spectra, the reconstructed spectra at these discrete frequencies omega k is equal to 1 by 1 minus a into e power minus j omega k is also equal to the sampled version of the original Fourier transform. However, in general, they are not same. That is, when for frequencies which are not equal to omega k, the structure is not exactly identical. So to summarize, in this video we have looked at the sequence x of n, which is defined as a power n u of n, and its Fourier transform x of omega given by 1 by 1 minus a into e power minus j omega, and then sampled version given by 1 by 1 minus a into e power minus j omega k, where omega k are 2 pi k by capital N, and k is from 0 to n minus 1. And then the sequence corresponding to this x of omega k, that is the sampled version, is given by xp of n is equal to this periodic sum, which is simplified to be equal to a power n by 1 minus a power capital N, where capital N is the period. So this is an extra factor of 1 by 1 minus a power n due to aliasing. And then we extract the finite sequence from this periodic sequence of infinite length. So x hat of n is given by xp of n only from values of n between 0 and n minus 1. That is 0 and n minus 1 are included. So x hat of n is a power n by 1 minus a power capital N for n equal to 0 to n minus 1. So we can construct the Fourier transform of this finite sequence. So x hat of omega is found to be equal to 1 by 1 minus a power n into 1 minus a power n into e power minus j omega k capital N. The Fourier transform is given by x hat of omega is equal to 1 by 1 minus a power n 1 minus a power capital N into e power minus j omega capital N by 1 minus a into e power minus j omega. So that is the Fourier transform of the discrete sequence x hat of n. Now when we sample this Fourier transform, that is x hat of omega k, we find that it is actually equal to, again, a simple expression 1 by 1 minus a into e power minus j omega k, which is found to be equal to the sampled version of the original Fourier transform. So these Fourier transforms agree only at these discrete locations. That is the Fourier transform from the original sequence x of n and the Fourier transform determined from the this spectrum, that is determined from x hat of n, that is the finite sequence extracted from xp of n. So this is the influence of frequency domain sampling on the spectra, that is on the reconstructed spectra. Thanks for watching.